Uh, that particular point is what we actually refer to as the equilibrium. Okay, so equilibrium is just actually the rate at which the forward equals the backwards. So the forward change equals the backward change. In terms of reactions, it is where the forward reaction equals the backward reaction. But as it is here, what we are actually looking at is phase shifts. So a solid is changing into a liquid. This is the line that is demarcating that. This side is a solid side, this side is a liquid side. So should the rate at which the liquid changes to a solid and the rate at which a solid changes to a liquid equal, that will happen along this particular line. So these solid lines are actually showing us phases where equilibrium, points where equilibrium is likely to be when the changes are happening. Therefore, let us look at how this can be interpreted. Okay, so when you have a pressure of 1 atmosphere, the pressure of 1 atmosphere is actually the pressure of 1 atmosphere is actually the pressure of 1 atmosphere will give you the normal boiling point, melting point of a molecule. Okay, melting point and boiling point will always happen at 1 atmosphere. When you are warming something, when its pressure rises and equals the atmospheric pressure which is 1 atmosphere, that particular substance, if it is a liquid, will start boiling. If your temperature is rising, it will reach a certain temperature. That particular temperature at which the pressure will equal the atmospheric pressure, your substance will begin to boil. That boiling that substance is going to have is actually what is going to be referred to as the normal boiling point. So the normal boiling point should happen at standard temperature, which is atmospheric temperature, which is 1 atmosphere. Now, this particular phase diagram has different spots, as you can see. It has this point here where we have these 3 lines joining to form that particular point. So this particular point here is called the critical point. Okay, that is called the critical point. So critical point is actually the point where your substance exists in 3 phases. At the critical point, you will find your substance existing in 3 phases. It will be in the liquid phase, it will be in the solid phase, and it will be in the gaseous phase at the same time, at that particular point. So the pressure and the atmosphere, the pressure and the temperature at which that happens, they are called critical temperature and critical, triple, not critical, sorry. That's the triple point. Not critical, but the triple point. This is a triple point. The critical point is that particular point there. Critical point is a point where your gas can no longer be compressed. Okay? Your molecule is no longer a gas, it becomes a superfluid. Okay? At critical temperature. So this temperature and pressure, 78 atm and 31 degrees Celsius. This is a critical pressure, temperature, and that is a critical pressure for carbon dioxide. Beyond this particular point, you cannot compress carbon dioxide. Carbon dioxide becomes uncompressible. So this particular point is what is known as the critical point. So at critical point, your gas becomes uncompressible. So once your gas goes beyond the critical point. You can't compress it. The triple point, your molecule exists in all three states, in all three phases, solid, liquid, and gas. And then you have, of course, this particular 1 atm there and temperature, which shows the normal boiling point of your gas, your solid, to say. So let us look at how we can now apply this picture in answering these particular questions down here. So assuming we live at sea level where the atmospheric pressure is 1 atm, how could carbon dioxide be liquefied? So how would you turn carbon dioxide into a liquid? Okay, so you have carbon dioxide, a gas here. How are you going to turn it in a liquid? Okay, you live here. How would you turn carbon dioxide into a liquid? So turning carbon dioxide into a liquid will entail that you increase the temperature as well as the pressure. Once you start going up, you are increasing pressure. Once you start going this side, you are increasing temperature. So increasing the pressure and increasing the temperature, say if your temperature is somewhere around 10, so 10 will be somewhere there. If you raise the temperature to about 10, okay, and you rise your pressure to about beyond 5.1, so say 6, you're going to find that these are going to meet in that particular area. And this area is the liquid area for carbon dioxide. So if you live at sea level, for you to liquefy carbon dioxide, you need to increase the temperature as well as the pressure, both of them at the same time. If you keep atmospheric pressure, you can never liquefy carbon dioxide, because irrespective of how much you will reduce the temperature, your molecule will just sublime. No matter how much you increase your temperature, your molecule will never turn from a gaseous into a liquid. So this is only going to be possible once you increase the pressure, you also increase the temperature. And I've given you an example for an illustration. And then from here, you have at what temperature and pressure does dry ice sublime? Okay, at what temperature and pressure does dry ice sublime? So you don't need to start making figures of your own and stuff like that. Just come here, 1 atmosphere and temperature of -78. This is a gaseous, this is a solid, this is a gas. Anywhere along this line, that change there, your solid is changing into a gas. That's sublimation, that's sublimation. But why should you start looking for values which are not on the table when you actually have values that are on the table in the range you are looking at? So here, at what temperature and pressure, at 1 atm and a pressure of